welcome for this new day of this conference. My name is Mattia De Rosa. I'm the University of Genoa. We met yesterday briefly during my welcome speech, which I will do it again today. Thank you very much. I'm the coordinator of the SHERLOCK project. I just give you a very quick overview of what is SHERLOCK, and then we will have an interesting agenda with very important, distinguished keynotes, and then in the second part of the session, of this SHERLOCK session, we will have different papers that comes out from the work that we did during our project. Just a few words about SHERLOCK. SHERLOCK is an Erasmus Plus project funded by the European Commission. It started in 2023, in September 2023, and is focused on buildings, so our buildings renovation. The main goal of the project was to put together expertise from a technical subject related to the building renovation system and the financial world. So the idea is to bridge the gap between the technical aspect of a building renovation framework with the financial instruments that are capable of supporting this renovation. During the project, we try to conjugate the research that our institutions are doing with some educational aspect. Have you seen probably in the lobby some presentations, some slides, and there are some QR codes that you can use if you are interested in knowing more about what we did. Basically, we try to conjugate the research with education. So we created a new framework, a new educational framework, which was aimed to support the upskilling in this field by bridging this gap between these two worlds, the technical aspect, so engineering, architects, so the people who design the energy systems and the renovation strategies in buildings, with the financial professionals. So all the subjects related to economics, business analysis, and so on. The idea, as I said, was to bridge this gap. So try to provide skills at multidisciplinary skills in both sectors. As I said, I don't want to bore you too much about this. I mean, this educational programs is available on our website, and we use different tools that you can explore. Like we have some case studies, we have some micro credentials, so short courses that you can freely look at in our platform. All the information are provided in the QR code that you can use that are shown, are displayed in the lobby. I just stop here. If you have any more questions, of course, about the project, I will be happy to answer them. I think we are here to start to listen to our keynotes and to see the research that has been done during these 3 years. So there is a little change to the agenda. So I want to introduce our first speaker, who is Dr. Amy Fay from Maynooth University, who will introduce us into the educational framework that we used in our project. So thank you, Amy, for joining us. Please, the floor is yours.
Thank you. So what's very interesting about the SHERLOCK project is the stakeholder engagement aspect of the work. And this is very much largely led by the 3 o'clock partner on the team, so I can't take credit for this. But I will just share the experiences from kind of the Irish perspective as well, of engaging in this kind of process. So we asked ourselves at the beginning of this project, who needed to be involved in the designing of learning materials and resources for for the overall project. So we started out with a quadruple helix stakeholder approach where 3 o'clock set up knowledge hubs in each of the different partner countries. And those knowledge hubs were really the most important aspect of this project because they were the vehicle for bringing stakeholders together. So stakeholders from the education sector, from industry, from policy making, and then learners themselves, in addition to educators, to help to co-create from the very outset of this project what it is, what we wanted our micro-credentials and our learning resources to look like. And this is really important to have this multi-stakeholder approach because it gave us a lot of insight into what learners actually would need and what would be useful for learners, but also what would be useful in terms of policy implementation and filling future knowledge and job gaps. So we didn't just look at, vocational educational training, secondary school, tertiary level. Overall, we have taken an approach where our dissemination work has incorporated data collection and knowledge development as well. So right from early years education all the way through then to the adults of this world who are creating policy in this area. You can see a picture of a Lego city up here. So initially we thought this would be nice to use as a dissemination activity, but in fact, all age groups love Lego. And so this Lego has traveled around to many different locations and has been involved in SHERLOCK activities with over 50,000 stakeholders across the last 2 years. And it's a really remarkable way to interact with people. It was fantastic for us to get conversations started about complex topics around financing in the building sector. It's not a topic that you hear and you go, if you're an engineer, you're in finance, maybe it's like, oh yeah, that's my bread and butter. But for most people, it is a complex topic. And if we're wanting to engage with civil society and educators that are actually going to be working with students, we want to make it approachable. We want to try and involve them in a way that is meaningful. So we had events in the different knowledge hubs for early years, as I said, right through to university level, and for external industry stakeholders as well. And that was really important in terms of gathering feedback for the designing of the different micro-credentials and then micro-programs in the project. So it's a continuous loop. So we had the design stage, testing then with intended users, iteration, so incorporating feedback from those users, and then dissemination. And most people think, okay, dissemination, we're finished, the project is done. But actually, dissemination is a great way to learn more and to work on the sustainability of the project. So we have these great micro-credentials. How do we interact with people in terms of how can you use them? How can you incorporate them into your teaching? They're there on a platform. Fantastic. But how can we speak to educators and industry stakeholders about how they might incorporate them? So in terms of the different activities that we involved our stakeholders in, obviously there's different levels. I like this model, the avocado model. Not everybody needs to be involved at all stages of the project, but 3 o'clock were very clever in terms of crafting the stakeholder engagement with the knowledge hubs in a way that was meaningful for the different stakeholders that were involved. So for instance, we have the inform stage, so just informing people about SHERLOCK, being out there, being at different events, and then the consultation stage. So at this point then, it was very important to gain, to think about issues that were relevant for the different stakeholders and not just us as, I was going to say Mattia as a project coordinator, but what was important to the prospective learners in terms of the skills that they needed to develop. And from this came some very interesting insights. So it wasn't just around, harder skills in finance and engineering, but also some of the more softer skills that we really need nowadays to solve complex societal challenges, such as financing in the building sector. And I think one of the micro-credentials that I want to mention as a result of this, it's coming up shortly in the slides, is the systemic design for energy retrofitting. And that was one that in Ireland we promoted quite heavily amongst our different stakeholders. This was one of the micro-credentials that was developed. It was developed by 3 o'clock, and even the very approach to developing a micro-credential like that, involving different societal sectors, that's something that it wasn't something I experienced in school, interdisciplinary learning to that extent. So I think it can be extremely useful for any type of audience. And that's what really makes Sherlock unique, is that the micro-credentials are very relevant for people from different backgrounds. And that's really important, that we're not siloing when we're addressing this sustainable energy transition. So with our younger cohorts, some of the interactions that we've had in the Knowledge Hub, at least in the Irish sector, we've reached over 32,500 people in this is last year, I think. And from some of these activities, we've piggybacked other activities, and we realized inclusion is a big challenge in this sector. And we have to ask ourselves always, who needs to be involved and why are they not involved? How can we engage with people at their level? We've engaged with over 500 industry, government, and academic stakeholders, and there's been over 1,300 students already have completed the micro-credential courses. And I mentioned how we engaged with people. You can see here there's secondary school teachers, we visited schools, vocational education training providers. We had workshops in the universities, boot camps, where people were able to interact hands-on with different concepts relating to sustainable energy transition and financing in the building sector. And then we had policy roundtable discussions with people from different sectors, because it's not a one-stop shop fits all. So having those different sectors and different stakeholders involved was really important to us. And overall, this really helped us to design resources and create knowledge hubs that will allow for longevity in terms of the relationships that have been developed, and allow for other projects and ideas to emerge from the learnings that have come from that. So I mentioned the 3 o'clock one. The continuous loop is absolutely crucial in terms of this kind of work. So the testing, the iteration that was carried out. And overall then, I think in terms of the Sherlock project and the platform that has been developed, we've gotten to the point where it's not just the Sherlock team anymore. The knowledge hubs feel that it is a project that belongs to them at this point, and they're using these resources. We're getting people getting in touch with us saying, is it okay if I share these micro-credentials, or if you could come and give a talk about the work that Sherlock is doing and the different kinds of micro-credentials that my employees might use in terms of reskilling and upskilling. They're all free to access, and we might share a link potentially at the end. But what we should be asking at ourselves, everybody in this room, any sort of work that you're doing in this area, especially where it's a complex concept, who is not in the room and why are they not in the room? So even the conference that we have today, it's open for civil society members. I'm not sure how many civil society members we have, but we need to be asking ourselves, in terms of sharing, in terms of involving people, how can we do that in a way that is meaningful, that is going to meet them at their level? Then we will have new jobs that have been co-created by all of the different sectors that are involved in society, giving society ownership of this transition and not leaving it just with the quote-unquote experts. So that brings me to the end of the presentation. Thank you very much, and I hope that you have an excellent rest of your conference. Thank you.
Good morning from my side as well. So thank you very much for being here. Sorry, the series speaking as well. So let's go a little bit from build environment and micro-credential to city level. And we have the first keynote speaker, Professor Paulo Ferrão. Let me introduce some words about Professor Paulo Ferrão for those that don't know him. Distinguished professor at the Instituto Superior Técnico, University of Lisbon, president of INMAI Center for Innovation, Technology and Policy Research. He is a board member of Eureka Association and former president of Costa Association. He has been president of Fundação para a Ciência e Tecnologia from 2016 to 2019 and director of MIT Portugal program from 1996 to 2016. He is a member of the Environmental Advisory Committee of Rolls-Royce. He has been active in sustainable, and he is still, I think, sustainable cities, where he co-authored a book of MIT Press on sustainable urban metabolism. He is also a member of the European Commission Mission Board of Climate Neutral and Smart Cities, and he has been engaged with U.S. National Academy as a member of Sustainability Roundtable, the commitment on sustainability linkage in the federal government, and the Committee of Pathway to Urban Sustainability Challenges and Opportunities for United States. He has been leading the urban project component in 2 ADB projects, for which the publication Urban Metabolism of 6 Asian Cities emerged. Professor, it's an honor. Please come and.
Well, good morning, all of you. I'm very happy to be here. I would first like to thank Laura for the invitation to be here. And I would like also to thank Amy to make the previous presentation, because let me start with this. I believe that we are Europeans with a mission. So all of us, so I believe in this room, we have this mission to promote zero carbon built environment. And I'm going to speak to you about a mission. So indeed, as you know, there are 5 missions in the European Commission. So one of the missions is this one. So the mission to promote climate neutral and smart cities. And I have really the honor nowadays to be the chair of the mission board at the European Commission. And this is important because we are making use of all the knowledge that we are providing of SHERLOCKs, of WeGenerates, of everything that we are doing, and working with our cities to put it in place. And that's the story I'm going to tell you a little bit about. So the European mission, for those which are not so much aware about what it is, that was an idea that started in 1999, when by the time we at the mission board proposed the Commission to support 100 cities that would like to be climate neutral by 2030. So by the time, this is a great challenge, and 377 cities applied, and the Commission has selected 100 cities plus 12 cities from neighboring countries. So we had these cities with the ambition to become climate neutral by 2030. So these cities are represented here. So you can see the cities in your own countries, which are mission cities. And what was to be a mission city? Well, basically the mission city has to do 3 things. First, the mayor has to say, yes, I want this. So this is the commitment. And then they have to establish an action plan. So what are the actions that I'm going to take? And then they have to do the third part, which Amy also mentioned, and I think it is a big focus and a very important one in SHERLOCK, which is to say, well, where how do I finance this? So where do I get the money? How do I put this running? Well, and then this is what is condensated in a document that the cities need to present to the Commission, which is the Climate City Plan. So the Climate City contract is presented to the Commission evaluates it, and then if it is okay, the city gets the seal of the label of Mission City. And then it has, of course, to still fulfill its pathway. And this is what it is to be a mission city, and this is that to say that the cities work as lighthouses to the other cities. So how can we do? So let's navigate a little bit into this. So what I will bring to you, it's a different type of research, so which is to look at the climate city contracts that the city have presented and what were their practical findings. So what did the cities find? And well, basically, so the climate city contracts are organized in 5 areas. So decarbonization of the energy sector, decarbonization of the transportation and the mobility sector, decarbonization of the building stock, moving from a linear to a circular economy, and then of course compensating for residual emissions. So there are always at the end of the day emissions that you cannot avoid, and then you can compensate, well, for example, forestry or even active methods of compensation, carbon capture. Well, I will now focus a little bit on the building stock, which is our matter here today, and what the cities have found, and they have in their action plans highlighted actions like, for example, massive building renovation and refurbishment. Of course, it is a priority, obviously. Fighting energy poverty, well, especially in vulnerable households. Electrification of residential and services consumption, and of course, local harvesting of renewable energies, which is to say, make use of solar and wind at an urban level. Well, I'm going to pass quickly through these, but cities, of course, have found many different barriers and opportunities. So among the barriers, let me say that some of them are very obvious today. So there is a tremendous skilled labor force need. So we don't have the skilled labor force to promote the rehabilitation that we need at scale and in time. And there is a lack of energy-oriented refurbishment. Many times even so, when you do refurbishment, it's more aesthetical than energy efficient sometimes. And of course, there are the problems of multi-governments and always the problem of financing. But there are, of course, different opportunities, and one of the main opportunities, and I will speak a little bit about this, is on digital twins. So what is the problem today? And I'm sure you are discussing this in your conference. If we want to harvest the renewable energies, the problem is that, of course, they are variable in time. So, and they are variable in place. So it's no longer good to say that we have averages of, in average the energy is like this, in average the energy is like that. No, this is not enough. So we need to have modeling of the energy consumption in buildings, in each building, and in each 15 minutes at least. So that's more or less the norm. And that's why we need the digital twins. For example, that's part of the work that I do. Today I don't come here to say very much about what we do, but just to call the attention, as it was mentioned, that of course these digital buildings, digital twins of buildings are very important because we simulate the energy consumption in building, and then we simulate the impact of different actions in the building stock, like for example, insulation, putting PVs, changing the windows, etc. And what we do is then to calculate the cost benefit of each action. Then this of course supplies the action plan of the city, for example. And then, of course, we have also work on mobility related to buildings. So we have developed an interesting method, which is to say at the door of each building, considering the socioeconomic reality of the people that live there, and the distance, for example, from a bus station, does the person have money to have a car or not? Is this a place where you can put renewable electricity, renewable energy, for example? We define a combined index, and then we say, well, how much is the mobility poverty in that region, and then we map these to provide data to facilitate policy on mobility, but associated to the building, to the site. Well, and then, of course, to energy communities. So if you model each building at each different time, of course, you can plan the energy plan in a certain neighborhood, in a certain region, and of course, this is also very important for building energy communities. Something which is, of course, very important is to say, well, if at the end of the day, your work is very successful, and buildings don't consume any energy at all, which is the energy that buildings consume? It is the energy that is embedded in their construction materials. So it is the embedded energy. And then our digital twins also work on looking at this embedded energy, and more, we work with the BIM software to design buildings to be recyclable, to be reusable, to have different components, to be modular, and of course, this is another dimension for the digital twins. But okay, I would like to come back to the mission, the European mission, and to provide you some very, very new result that I didn't even publish, so I just started to do this, and I would like to share this with you. So what we did, what I did here is to look at the climate city contracts of 25 cities all across the Europe. So they are fully representative of Europe, to read them, to study them, and to tell, well, what are the problems that cities are facing. So, and I came to the conclusion that cities report, not me, cities report, so I just organized the information in my way, of course, but cities report 7 problems. So the first problem, Amy already mentioned, everybody mentions this, is that you cannot run for sustainability in a governance which is siloed. So there is one that takes care of transit, there is another one of buildings, there is another one of energy, there is another one of water. It's very difficult to create a policy of climate neutrality. The other is multi-level coordination alignment. So cities have some control of the situation, but then you have regions, you have the nation, you have the European Commission. So how do we work together if we are not aligned? And that is the power of what we all are doing here. And I'm so proud to be near these standards, because they say we are Europeans, we have a motivation, so we have a common policy. And I think this is really the only way to go forward. And it is so special nowadays, you know what I'm meaning. So, and it's really precious, we should esteem it. So, and then of course, we need to finance. So how do we finance this? We need financial innovation. So we also need a lot, the economists and everybody, to be engaged in this. Not only economists and people that do financing, companies, stakeholders, different private stakeholders. We need to bear in mind that in the investments that the city needs to do, not more than 5, 6, 7% are done by the municipality. So all the rest is done by companies or by us as private citizens. So, of course, we need technical capacity in data. Thank you, Sherlock. So you are working on that. That's very important. So we need stakeholder participation and co-creation. Again, how can we engage the companies? How can we provide trust? So how is someone going to invest, for example, in building rehabilitation if the law or the permits are changing from place to place and time to time? Nobody will. So we really need to convene the stakeholders. Mission cities are promoting this in different types of coalitions and so on, but I will very briefly, of course, mention this in a minute. So we need ecosystem coordination and partnership. And of course, we need climate justice and social acceptance. So we cannot do these things against the people. We cannot do these things without the people, because then they will turn against us. So look, for example, a very simple thing. Try to forbid traffic or cars, private cars in the center of a city. I was just living for 3 months in Madrid, and it was an interesting experience. So this is difficult. If the people is not involved, we'll always have the people against you in a thing that at the end of the day will benefit them. Well, so these are the challenges, just to bring these to your mind. Now, I would invite you, you should not, I would invite you to read at least one climate city contract. So that's where each city states how they are going to solve these issues. And what I'm going to do now is to read for you the 25 cities, the climate city contracts, and to bring to you which are the solutions that different cities are adopting to solve these challenges. Not all the cities solve all the challenges, but they pick one and the other. So, and that's what I will do now. So cities are using 6 solutions, 6 governing instruments to provide solutions to these challenges. So now, from this moment to the end of the presentation, I have 6 slides, which of course bring to you some elements of each of the tools, the governing tools. This is all about governance. And here I would like to say, technology is there. What we need is governance. So how do we manage this all together? So, and let's go. So first one, we need mission governance structures. So how does the mayor organize this to take out the silos? And they are doing different things. So for example, they are promoting, for example, working groups, working thematic groups. They are promoting stakeholder and city advisory forums. They are promoting technical support units. Well, so basically what they are trying to do is to create a cross-cutting section across sometimes is, for example, they have one person, which is the climate change leader, of which, so for example, when you make an investment, you need to have the approval of this person, or you create a group of them. So, but this is important. They are creating different elements of this. And then you have a big problem. There is a word that for sure economists know very well, and I would say this is a terrible word, which is a project needs to be bankable. And this is, of course, a very big nightmare for any city. And just to give you a very pragmatic example, this goes better with examples. For example, basically, it's not a rule, but I will give you a figure. So it's very difficult, for example, a city says, okay, here I have some projects, and I go to the European Investment Bank. But the European Investment Bank will never finance an investment with, I would say, less than 50 million euros. So, well, small cities don't have a lot of 50 million euros projects, but they can group them. They can organize them. And this is what it is in these slides. Cities are working on this. So portfolio management, so project portfolio management. So they are bringing together the projects, they are making them sense, they are making them bankable as a whole. They are creating what is represented here, which is in fact a place where you see the progress, you see the results. And of course, this is very, very critical for project advancement in the cities. So another one is to create integration instruments. So you need to align public and private financing. So, and this is of course very difficult as well. So as I was mentioning before, you need to attract the privates. The municipality is only responsible, as I said, for about 7–8% of the investment. All the rest is companies that need to do it, is us as privates. So you need to find the way, and in order to find the way, you need to bring new and innovative financing. So, and then, of course, I'm an engineer, I'm not an economist, but you will get into tools like, for example, green bonds, blended financing, private public partnerships, and this is what cities are developing and working together with well, banking institutions, together with private stakeholders. And our work will not go off the ground if this is not working in reality. And then, of course, you need to have technical capacity. So the municipalities are relatively weak in technical capacities. And of course, again, I'm very happy to be here supported by SHERLOCK and others, because really we need to provide, to come for technical support and a lot of support with data. So we need to monitor, we need to understand where the problems are, we need to see progress. And of course, this requires a great effort, and multiple contributions needs to come, and I'm very happy to be here because I'm sure you are providing much of this to our cities. And of course, this is super important. And then maybe the most difficult, to bring people together. So how do you bring together the citizen? How do you bring together the private investor? There is no other way. You need to put them in a table and to co-create solutions with them. And here are examples in this slide. I just don't want to overcome my time allocated. But of course, you need cities are making these, putting the stakeholders together and really co-creating solutions. It's very smart, because if people see this as their solution, well, there is a much higher probability they don't fight against it at the end of the day. So this is not only that, but of course bringing to the attention of all of us, and I was really, for example, yesterday in a totally different conference, but where it was very much highlighted that many of us live in a bubble. So there is many people with many problems, and if their problems are not heard, if the solutions are not worked to take them into consideration, and to this very, well, trendy, famous word, so they leave no one behind. So it is the moment to act on this. Okay, so that is why your work is so important, because of course it is also a form of bringing people together. And of course it's very important, and it is the purpose of the mission, is to make sure that your work goes into the mayor's office, goes then into the investor's office, and of course is shared and co-worked with the people. So this is very, very important. And at the end of the day, we'll contribute to something which is critical, to eliminate regulatory barriers. So, and to create different elements. Please do also think about that, reflect about that, and bring solutions. It's not only the technical parts, it's to identify, well, sometimes there is this or that regulation that is causing so much trouble. This is, of course, the last piece, the last tool, which at the end of the day reminds me all the days, I think, when I wake up, minded to come to a conference like this. And here today, I'm really very pleased. We are Europeans with a mission. We want to contribute to our society to be climate neutral. And we certainly know that one of the major contributions is on the built environment. So I think we are really contributing and aiming at this greater objective that we have in Europe. So thank you very much for inviting me. Thank you very much for your attention. And above all, thank you very much for your work. Thank you.
Thank you, Professor Paulo Ferrão. I think we can accept a question if from the audience. Any questions? Thank you. Thank you so much. I really enjoy your presentation. I'm Veronica Subarto. I'm from Australia. There's so much I think Australia can learn from this. I don't think in Australia we have the mission where different cities get together and trying to achieve this goal. And I think there's a lot of lessons learned that I can bring back to Australia. But my question to you, and actually somebody else asked me this question yesterday after my keynote, and saying, I can't remember who said it, and if you're in the room, please to let me know. So she basically said, what we address a lot of time is how we can, one of the mission is to increase or to reduce energy poverty, to make sure people in poverty, they still achieve good built environment and so on and so forth, which is, I think it's really important. But what she said is, we never really address the other side, which is the rich people. And which is true. I just read the paper from Nature Sustainability that says 10% of the population, which is the rich, actually produce 2/3 of the greenhouse gas emission. And their carbon emission actually even 6.5 times in terms of the per capita of normal people. So my question is, how does the European
mission also address this issue that, we don't only just try to help the poor, but try to address the excessive emission that the rich actually are producing. Thank you.
Yeah. Well, look, there are, these are, well, at least they have a name. So, and I would like, is the art to get. I don't know if you knew this. So this is the art to get. And the art to get are the people that are, for example, very poor and that you don't, but are also the very rich that don't care about this thing. So at least they have a label and people are looking at that. But then, of course, this is a very, very difficult issue because it plays with the social organization that we have now. And we know that the world is not becoming more equal. It is becoming more unequal. So, and of course, but I would also say that eventually more in places out of Europe than in Europe, but also in Europe. And I was yesterday in a different place, and I think, and of course I don't have an answer to you, so that's the obvious thing. But I think we are still in the moment where we need to provide our attention to provide to the poor. So I don't know if you agree with me, because we don't have the mechanisms, enough mechanisms to address the rich. And this is basically political, because there could be mechanisms. So you could, I don't know, tax, increase prices, but we don't see the world going in that direction. So I don't see it going in that direction. So, well, I'm not going to start speaking about things that go in my heart. It's not my role here today. But of course, it is very difficult to say. Let me just say one thing. Why do we have our whole system based, for example, in taxation of work? So why do I pay? So do you think I am a rich guy? No. So do I get my salary as a professor and I pay 48% tax? If I was a millionaire in the stock market, I will have paid 28. Is this correct? I don't know. So, but these are totally, so these are, I think, issues that are of prime importance, but in my humble work, what I think we are still on the stage of providing to the ones that need, and then, of course, on addressing the change in a way they are not affected, which is really the just transition. This was, and then, I don't know, so we need to work together on that. So it is certainly easier to work pro something than against something. So, well, but I'm very humble to, humble, no, I'm resourceful to solve the problem. We need to solve it as a society. Well, the only thing is, of course, the last slide, to engage people, to have people motivated to these causes, for them to understand this and to fight all together to a certain purpose. And that's why I am so passionate about a mission. So if we don't have a mission, it's everybody to each side, and we cannot organize ourselves. So that's how I defend missions so much at the European level, at least. And that's why, and let me tell you very clear, so I don't speak for the European Commission, but I am absolutely sure, so I've participated in different forums, for example, with Japan. So the European Commission is very interested in, of course, sharing with other regions in the world these experiences, and of course, that's another way, I think, where we could eventually become stronger. Yeah. Sure.
Yes, and actually, thank you very much for the presentation. And my name is Denia Kolokotsan from Technical University of Crete. I really like the way you approached the previous question, because my question continues with the stakeholder engagement and this. And I'm also wondering, because in the previous presentation, we hear that how we involve all, and I think in that question, we are very much biased.
Yeah.
So I want your reflection on that. How we involve all? Because, okay, we say that we involve all, but are we involving actually all?
No. No, we aren't. That's very clear. So, and it is very difficult. So, and it is very difficult. So there are different mechanisms. but there, so for example, when you create assemblies of citizens and you listen to them, or you create these apps where you ask the citizen what they need, or you have these participative investments, but they are still small scale, so they are not changing the world. But again, the major question and the reason why a politician needs to involve all is to get support for his policies. So I think this is the basic thing. So if a politician does not engage the population, he will not get their vote. Now, the politician needs to have the time and the dedication to start this movement. But I'm a little bit hopeful because I see that in different ways this is working, and for sure I'm already an old guy, so I'm not so much in this, you know, I don't even know how to say TikToks and, but there are now these new ways to engage people. So it's not certainly on conferences like this that we will get them. So we need to work with them. We need but we need to dedicate effort to that. So it will not happen, well, just because we are here saying it will happen, but we see it going on. And you know, just to go again for the mission, the best way, in my opinion, to engage people is to demonstrate by example. So for example, now I was very struck with Madrid, so I've lived in Madrid for the last 3 months in a kind of a sabbatical, and I was really very impressed. So, as you, I don't know if you know, but for example, I tried to take my car. I could because it's electric, but you cannot take a combustion car to Madrid. You cannot. You are fined. So, of course, there was a revolution, I guess. It was a big problem, but now people is happy with that. So, and if you have examples like this to say, well, look, there is a little bit of pain, but at the end of the day, it pays off. And so that's why we have the mission cities. So the mission cities should highlight, should be lighthouses of different experiments that then the people should visit and should see. And so, well, if it has worked here, eventually. So, but how have they done it? Which were the major pains? Which are the problems that are still not solved? Well, I'm saying this, but I saw a lot of Ferraris in the center of Madrid. So, in a way, I don't know. So it still accommodates a little bit of difference. Well, I'm not responding because, of course, the questions are very difficult. But I think there is hope. And I really believe in the missions and in cities that are lighthouses to help us looking the way forward. Yeah. Thank you so much.
Thank you very much, Professor Paulo Ferrão. So now we will go to the next keynote speaker, Professor Christoph Markides. Let me introduce. Professor is Professor Clean Energy Technology at Imperial College London, Head of Clean Energy Process Laboratory and leader of the Experimental Multi-Phase Flow Laboratory, the largest facility of its kind at Imperial. He served as editor-in-chief of Applied Thermal Engineering and founding editor-in-chief of the new journal IE Thermal Fluids. Professor Markides is internationally recognized for his work in applied thermodynamics, fluid flow, heat mass transfer with high energy performance technologies for energy recovery, utilization, storage with a strong focus on solar thermal conversion, author more than 30 publications, and his contribution have been recognized with numerous awards. Professor, please welcome to our conference.
Thank you, everyone. Good morning. Thanks for coming to my talk. So it's a little bit of a change in gear. My talk is very technology focused. My aim over the next 20 minutes is to show you, I guess, options that we have for solar energy conversion, which don't involve things that most people know, so conventional PV panels and solar thermal for hot water heating. So we had that introduction, so I'll skip this very quickly, but I just wanted to let you know that there's a new journal, just that part of the slide is the relevant one, which is called AI Thermal Fluids. If anyone has an interest in the development and application of artificial intelligence methods to these types of systems, I'm around, so please come and find me and talk to me. I'll tell you about the new journal. Okay, so we have a spin out. I just wanted to tell you that everything I'm going to show you today is kind of linked to this activity at Imperial. If anyone, especially the younger people, have an interest in entrepreneurship, translation, come and talk to me about how you spin out a company and what we can do there. Okay, so let's start. I want to tell you about what is this PVX. Before I go to PVX, I want to start from the classical technology, which is called PVT. I hope many of you have heard about this. So if you replace that X with a T, that's quite common, right? So it's PV and thermal somehow integrated into a single component. Now, what's this PVX? That's a little bit more strange, right? So we'll get to that towards the end of this part. So how did this all start? People realized that photovoltaic cells, depending on which material you pick, exhibit something called a temperature coefficient, right? So they exhibit a reduction in their efficiency as they're operated at higher temperatures. If you go in the south of Europe, Spain, Greece, Italy, and so on, even my country, so I'm from Cyprus originally, and you put a PV panel outside on a hot sunny day in the summer, right, you're going to be off the chart here, right? You're going to be at 70 degrees. So the loss in efficiency that we have is very, very significant. We could be losing 20% of what the manufacturer says we should be generating, okay? Because the manufacturer gives us an efficiency at 25 degrees. So this motivates, I mean, this is a description of a problem, but it's also kind of telling us what we can do to solve it, right? Because if we can cool those panels, then we can recover some of that lost energy. So this is the motivation of PVT technology. The idea being that if we pass some cooling flow underneath the cells and we kind of cool them down, we can recover some electrical efficiency. And of course, well, okay, now we've recovered that heat into a stream, we can do something with that hot water or air or whatever it is. So it's been a big area for some time. It's attractive to people because you can co-generate. Yes, you can generate electricity and some kind of thermal vector you can deliver to homes. Okay. So these are a couple of designs. There are many different designs, many different flavors of this, but I want to draw your attention to, so I would refer to these as conventional designs, right? It's not just one, there are many different ways to have those channels and so on. But there's one common characteristic to all these conventional designs, which is that you try to have a very, very high conductivity or small resistance, if you want, between the photovoltaic cells and whatever fluid you're passing through the system, right? You want those two things. Or if you like, you want to have maximized heat transfer, right? You want to pull out as much heat as you can from the cells, okay? Now, of course, this is advantageous because, as we said, right, cooling the cells and removing heat by itself is advantageous, but it does have one disadvantage. And we'll come back to this later, but the disadvantage arises from the fact that the temperature of whatever fluid you're passing through there, air, water, sometimes refrigerants, so the temperature of that fluid is very close to the temperature of the cells. So cells in typical commercial designs like this are 3 to 5 degrees higher than whatever fluid you have passing through the system. Okay, so we'll come back to this. But remember, they're very close to each other. They're coupled. They're tied together. So many years ago, I started looking at this with one of my master's students, and at that time, one of the things that she did, Maria Gerando, so she's still active in this space, is we went and we found many, many products on the market. Some of these don't exist anymore, so this is a relatively old publication. We can update it, but the results will look the same. And one of the things that you realize is that all these products, right, different manufacturers, different designs, they seem to have some kind of trade-off with each other, right? Whenever a manufacturer tries to make something which is, say, gives us more thermal output, somehow we lose electricity. Whenever we try to make something that's better electrical, somehow we lose some heat, right? So there seems to be some trade-off between those two, let's say, outputs. And the first challenge that basically arises from this is, okay, can we have designs that do not sacrifice electrical efficiency to give us that heat? It's never a good idea to sacrifice electricity for heat because electricity, most people realize, is a more valuable energy vector than heat, especially low temperature heat. Okay, so this trade-off where we sacrifice electricity to gain some hot water is never really a good one for this technology. So can we break this compromise? Challenge number one. Challenge number two, heat has a value, and the value of that heat is also a function of its temperature, not just the amount of heat, right? So I think most people will realize that the higher the temperature of the same amount of thermal energy, the more things we can do with it, right? So thermodynamically, there's a better value to high temperature heat and low temperature heat. Remember what I told you before, that in these types of collectors, the temperature of the fluid and the temperature of the cell are very close to each other? So if I want to generate high temperature heat, I need to operate my cells at a high temperature. I have another conflict here. Thermally, I want to be at a high temperature, right? Because it's more valuable. Electrically, I want to be at a low temperature because I get more electricity. These two things cannot be done simultaneously in the same system at the same time. Can we break that conflict? Second challenge. So, what can we do, right? Well, I'm going to talk to you about a couple of nice solutions to kind of increase the performance of these types of systems. We always start from a PV, pure PV cell, right? Which means that we already have electricity there. Now we want to gain some heat by recovering thermal energy. The challenge being we want to get that heat but not kill the electrical efficiency of the PV panel, okay? So one thing we can do, right, to recover that heat is to reduce heat losses. On the right-hand side, you see that there are two major heat losses from these types of technologies. One is through radiation, so we lose all this heat out to the sky or the buildings around us, we radiate heat. And the second one is through convection, right? Now, the convection losses are kind of an old problem, and there's nothing really challenging there. You might have seen solar thermal tubes, right? Something is in a glass and we pull out a vacuum, so that reduces the losses to the environment. So we won't talk about that, so that technically that's something that we understand. But I will tell you a little bit about some very, very interesting coatings that we can apply to reduce this emission of heat out to the sky. So loss of heat for us is a problem, right? Heat is valuable, we want to retain it. PV panels don't care about heat. Yes, they're not delivering heat to anyone or hot water. But for us, we're delivering heat. Any loss of thermal energy is a loss of something valuable. So how can we suppress, stop this heat loss to the environment? The interesting figure here is on the right-hand side. We basically, what we want to do is we want to reduce the emissivity of the cell, right? We want to reduce this radiation. Emissivity times some kind of constant times T to the 4 is, yes, radiative heat transfer. So we want to make this emissivity lower. And what you see there is a black line, which is a measurement from a commercial cell, and a red line, which is the measurement after the cell has been coated with something called ITO, yes, which is basically a selective surface that allows you to reduce emissivity at longer wavelengths. So this is some work that we did some years back, and you can see here, yeah, that's this ITO layer, and that's what have the effect on the property. But I want to caution that this is just a property of the surface, right? We still don't know what the effect at the technology level is. We still need to understand what effect this has on the efficiency of the actual technology. So there are more steps here. You remember that second challenge I told you about? How do we keep the temperature of the cell low but deliver high temperature thermal energy? And I told you that there's a problem because those two temperatures are always tied together, right? How can we do that? How can we break this, let's say, coupling between those two? Well, we can do it through something called spectral splitting designs. What is this? It starts by us realizing that photovoltaic cells, right, any material you want to take, any color you want to take on that graph, are sensitive to part of the spectrum, right? So only some colors, let's say, will get converted to electricity. All the rest of the spectrum is just hitting the cell and just causing heating without possibility of being converted, right? So the thinking here is, well, we don't need to send that part to the cell. Why would we send, parts of the spectrum to the cell that is not going to convert to electricity? Let's just send it somewhere else. So what we do here is we physically separate the cell from some kind of thermal absorber. We only send the energy that the cell can convert to that cell, and we send everything else to a thermal absorber. But now, because the PV and the thermal absorber are physically separated, they can also be at different temperatures, right? This is the kind of design rationale of spectral splitting. So that's easy to say, but how do we do it? There are ways to do it through what's called preferential reflection or preferential absorption, right? So in some cases, some colors will go through some kind of dichroic material. What this means is it allows some colors to be transmitted and some other colors get reflected. So we can physically separate the cell from whatever fluid we're trying to heat, right? In all cases, you can see that's what's happening, right? There's a fluid part, and then there's a cell part, and we try to keep them apart so there are different temperatures. Cell cold, fluid hot. So you can do that through reflection, you can do it through absorption, right? In some cases, you can absorb some part of the spectrum into the fluid to heat it up, and the rest of the fluid, the rest of the spectrum goes to the cell, and so on. So I'll just tell you a few quick things about interesting things in this area if you want to know kind of developments in this space. There's a huge interest, yes, in, of course, now developing these materials with these magical properties that sometimes reflect and sometimes absorb and sometimes transmit, right? You can imagine these are properties, and we have a lot of materials available to us, but also we have a huge discovery space, yes? There's a very big area of us finding new materials that have very good properties, that can do all these fancy absorbing and reflecting and transmitting that we want to do. And this is a good space for artificial intelligence application, right? So trying to have all this data to try to design these filters with good optical properties is ideal for, yes, AI-based design. And what we're talking here is designing potentially new molecules, right? So fluids that don't exist yet, we can invent new molecules which are good for these types of applications. So that's one thing. This is for absorption that I'm showing you here. So molecules, yes, absorb light at different wavelengths. Or we can do things that reflect. Yes, so here you see something called DMDs, which are dielectric metal dielectric materials. And what they do is they have this kind of interference with light where they reflect some things and they transmit other things. So you can see here that they're transparent to visible, right? We can see through them, but they reflect the infrared. So we can use these types of filters, right, to split the light and to have the PV cells in one part of our collector and to have some kind of thermal absorber at another part, which is a very different temperature. So what I'm showing you here is we haven't published this yet, but there are many papers like this. In this example, you can maintain the temperature of the cells, which are, yes, at the focal point of this parabola, at around 60 degrees, while the thermal absorber at the bottom here is in excess of 200 degrees. So we've created 140 degree separation in temperature, not 5 degrees that I was showing you before. Okay. And again, the questions are the same, right? We need to design the properties of these materials, right? The reflectance, for example, the transmittance, and so on. And then we need to go all the way to designing our collectors on the right-hand side to understand the real effect of material properties on the technology itself. Okay, so that was a little bit materialsy, right? More on the science side, more fundamentals. Let's move one step up. So I told you before, we can have these wonderful coatings that can control these losses, right? We can reduce these radiative losses out to the sky. So what you're seeing here is two tubes. On the right-hand side, the cells are nice and blue, and on the left, they look yellowish, right? Yellow-green. That's because the ones on the left have been coated by this material, right? So ideally, what we expect, we know that the emissivity is different because we've measured it, but what we don't know is what effect does it have on this collector, which is a PBT collector, right? There are cells inside, and you might be able to see some kind of pipes here, yeah, carrying liquid underneath. So we're getting hot water and electricity at the same time. And so here we can see what kind of thermal performance benefit we have, and the electricity, yes, has a little bit of a drop, but the benefit here I think is quite clear. And these are the challenges in this field, right? How do we get this heat without sacrificing this electrical efficiency? This is a spectral splitting design, and I'm showing you here results where we try to compare a spectral splitting PVT collector with a PV panel side by side, same conditions, outdoor conditions. And what we're showing here is, remember what the challenge that we started it, right? We always start from a PV panel and we're going to act on this to get some heat, but can we act on it to get some heat but not sacrifice electrical efficiency? That's really the goal here, right? If you take a PV panel and you reduce the efficiency, yeah, and then you say, well, okay, but I've given you some thermal energy, that's a very difficult sell, because most people don't want to lose electricity to gain some hot water. But this is promising, right? So you're not losing any electrical efficiency, and now you have some heat, okay? This is still low temperature, okay? So these are still hot water for domestic purposes, right? Space heating, domestic hot water, and so on. And here I'm showing you a case where we are going to very high temperatures. So here I'm showing you a collector, right? A PVT collector whose design details I can't really show you right now because they're confidential. I mean, I can tell you tonight over the dinner after the third wine glass, but for now I can't really say very much. But the point here is that you can see that some of this thermal energy, right, is being generated almost up to 100 degrees, right? So these are measurement points almost up to 100 degrees Celsius, not the 60 and 70 we were talking before. And this is a flat panel design. There's no concentration, no mirrors, no lenses. This is quite difficult to do, okay? And what I'm showing you here is that for you to design a conventional PVT collector that's going to reach close to 100 degrees, your PV cells would need to be operating above 100 degrees for you to do that. So what is the, I guess, the breakthrough here? The breakthrough here is we're delivering, now we went up to here, we could have gone higher, but it's water, so we don't want to boil the water, right? So we went to 98-degree hot water, and the temperature of the cells is more like, what, 50? I can't really read that, 50, 60, instead of 100 plus. Right? So we have a reduction in temperature of 40 degrees compared to what we would have had in conventional designs. Okay, now this is very exciting for me because a long time ago I realized that, and many people know this, hot water is a low-value energy vector, right? But what can we do which has a greater value? Right? What output has more value than hot water? Many things, actually. So, for example, desalination, right? Clean water is of significant value, more than hot water, yes? So we started thinking about, well, you know, is there some kind of way in which we can have a process that we can integrate within the device itself, not separately, right? We're not generating electricity, sending the electricity somewhere else, and then driving a desalination system. Okay, that's quite known. Yeah, it's not needing technology development to do that. Our idea is, can you take this thermal energy which is generated in the cells, remove the thermal energy to have some kind of process that's integrated in situ inside the device itself, to give you something which is a higher value output, leave the electricity alone. We're not going to touch the electricity, okay? All we're doing is we're taking the thermal energy and we're doing useful things with it, but not just heating up water. So what can we do? Well, I already I think told you one of the things that we can do is we can use our thermal energy to evaporate water and then recondense it. So basically it's thermal desalination, but inside a panel. Okay, this is not, oh, we take heat from here, we take it over there, we have a desalination system. This is in the same device. So what's exciting about this? Well, what's exciting about this is you have a panel like this, and then water is just falling out of the panel with the salt rejected. And of course, we have a very big advantage due to this process because evaporating water is a very thermally intense process. So you're taking all this thermal energy away from the cells to cause the evaporation. So you're cooling the cells, right? You're getting additional electricity compared to PV. So now we're doing better than PV, plus we have this desalination function all within the same device. For me, this is more interesting than PVT. Not that I don't like PVT, but I think this is something that's a very interesting and exciting area for us to move in, right? What other functions, other functions can we integrate within these technologies? Now, just like I showed you this, I don't have a lot of time. These thoughts are quite short, but you can start thinking about, kind of use that thermal energy for fuel production, for hydrogen production, there's a lot of things you can start thinking about. This X now could be desalination, could be whatever you want, hydrogen. It could be CO2 upgrading, yes? Conversion, sorry. It could be many, many things. And I think I'll just leave it there. And I hope you can engage with me after the talk. The theme being the same, right? We have this heat. What can we do with it? Yeah. Okay. Most of my talk so far was relatively low concentration systems, low temperatures. I mean, I did show you one with a parabola where I said the temperature was going to 200 plus. Okay, we tend to do flat, so non-concentration work in my team, but not exclusively. So here what I'm showing you is a system in Mexico where we try to modify a parabolic trough collector. So this originally is intended for just hot water, well, not hot water, high temperature. You can do steam, you can have an oil system here, you can raise the temperature to relatively high temperatures, but there's no PV in here, right? It's just high temperature heat. Yeah? And so what we try to do here is we try to replace this tube in the middle here with some PV cells. And if you look carefully underneath here, you can see that there are cells there. So now we've turned it into a PVT collector, right? So now we can get electricity plus some heat. And if you look at this one here, you start to see very strange colors, right? You see some pinkish, maybe some green somewhere. And the reason for that is because we go from conventional PVT designs to spectral splitting designs. We're trying to split the spectrum here, so different colors go to different places, and that's why you sort of see the colors. Yeah? So what I'm trying to show you here is that, yes, we are moving slowly to also relatively large-scale systems. I mean, this is a full-scale parabolic trough collector, outdoor testing in Mexico with our partners. So there's a lot of range, yes, of different technologies here. Flat plate, small-scale systems for domestic. This probably wouldn't be domestic, right? This would be more like industrial decarbonization. This would be more like heat for some industrial facility, yeah? Okay. So thank you to all of the funders and people, collaborators. And if you want to know more about PVT collectors and technology, there's a review paper that we published. Professor Calagiro actually is here in the audience. Anything that in this article that you like and you think is a good addition to the literature, I will take the credit. Anything you don't like, you can blame Professor Calagiro over there. Thank you very much.
Thank you very much, Professor Marquides, for a very interesting presentation. I mean, it was inspiring to see the advancement that we can that can be generated in this field. Are there any questions for Professor Marquides? Yeah. Sorry, it's going to take a while to get that.
Thank you for your very interesting presentation. My name is Pablo Gagoria. I'm from an energy consultancy based in Madrid. And we usually work with investment funds and banks that they usually invest in PV production panels and self-consumption, etc. And they always make the same question. They are very worried about maintenance. Yeah, because the best investment is that one that you don't have to touch. So the presentation you have shown is impressive, and the results increasing the energy generation and the thermal generation. So my question here is, of course, I know this still experiment and it still needs to be developed.
Yeah.
But do you envision that this will be easy to maintain, or this will require like a long way, I mean, many years still to develop, to find a way to easy to be implemented and maintained?
Yeah, okay. That's actually a very, very good question, very difficult question. So I should first say that, you know, there's a very, very long journey between, you know, concept, idea, TRL1 to product, you know, sales, maintenance, and so on. The market for PVT, these kind of conventional collectors that I spoke about, is existing, right? So you can go to the internet, you can type in, I want to buy a system. There's actually Spanish, quite a lot of Spanish manufacturers, French. Yeah. So this is an existing product, and the maintenance for those products are not fundamentally different from solar thermal and PV systems. This is basically a solar thermal system and you stack some PV panel on top. Okay, so conventional technology, the maintenance is not very different from other things that we know about. What is difficult, I mean, that doesn't mean there are no challenges. What is difficult is that on the PV side, the electrician that's going to go and do the maintenance doesn't really understand or really want water anywhere near it. Okay, so it's electricity and water, not so good friends. And on the thermal side, the people there are very comfortable with pumps and water and leaks and so on. But They're not really electricians. So here, the maintenance has to be done by people that understand both things, right? But nevertheless, the short answer is there's no fundamental difference to those two things combined into a single technology. So the maintenance is not fundamentally different. Now, if you go to some of the other things that I showed, because I showed a kind of a range of things, so not one, of course, some of those are lower TRL. And to be honest with you, we're not the right people to go all the way to production and maintenance. We work at universities, we have spin-outs, and we need to work with people that are going to go that extra step to think about these issues. Because doing desalination in a panel has different maintenance issues than hot water going through a panel, right? It's a very good comment, it's a very good question, and I guess the answer, it might not be sufficiently good for you for now, but it kind of depends on which one of all of these you're looking at exactly, and we need to do more work on that as we go up the TRL scales. That will become more and more important. So thank you, it's a good point.
Thank you very much for your presentation. Sorry, we need to proceed because we are a bit delayed. So thank you very much, Professor Markides, for your intervention. So thank you for our keynote. It was very interesting and inspiring. We will now proceed with the program, the SHERLOCK programs. So our first speaker is Professor Carlos Vargas Salgado, who will deliver a presentation called Smart Energy Management Model for a grid-tied PV system with batteries through a genetic algorithm, the case of a consumer. You also have an assistant now, so it's perfect. Say hi to anyone. Say hi to anyone. Hi.
Hi.
Hi. Please. You need to stay here, sorry, because if not, they don't catch you.
Okay, no problem.
Thank you, Giovanni. Thank you. Big applause.
Thank you, Mattia. Thank you, Giovanni. And thank you very much for having me here today. I'm going to start with my presentation, or our presentation today. I'm going to talk about the presentation, or the idea today is, imagine that we are talking about decarbonization. We are working with renewable energy systems. So imagine that we have a PV system. This is the case of a lot of people in Spain. We apply, in this particular case, to a flat. So we contract someone to install a PV system, okay? And this company installed the PV system plus battery. So far, so good. It is working, the PV system produces, but what if I want to improve the system? What can I do? Is that possible? Or the system is, if the system is working properly, is possible to improve in any way? So in this work, we have been working with a genetic algorithm in order to optimize a microgrid. This is a system composed by a PV system plus a storage system. Okay, so yeah, this is the idea today. So we are going to apply algorithm in order to decide when we have to use the storage system, decide how much introduce energy into the storage system or take energy from the storage system, and also we are applying demand response. Demand response, it means that we are switching demand, or we are changing the schedule of the demand in order to take profit of the PV system. Okay? So now this is our demand. This is the flat. We have some consumers, and also we have the utility grid. We take energy from the utility grid, and we have a meter. This is let's say the normal situation. Now we have this meter could measure energy. We can take the information from the database. We access to the database through the company, from the supplier of the company supplying the energy. We can take the energy every hour in Spain. I think it's in every country in Europe this is possible, or even every 15 minutes. But this is not enough. We need to measure the energy coming from our PV system. So we have our PV system here producing in DC. It's a very small scale system. We have, of course, an inverter to convert DC into AC, and this AC is sent, or this electricity is sent to the to the grid, to the grid or to the house. So additionally, we have a storage system. This is the storage system. So as you can see, this is a hybrid inverter. This hybrid inverter, this means that we can, or the inverter can manage both a storage system and also the PV system. And also we need more information in order to use the data in order to optimize the system. So we need to measure everything. So we measure in the inverter, we measure the energy produced, and also we measure the energy going in and out of the battery. So we have everything. So we have the energy produced by the PV system, and we also have the energy going to the house, and we have also the energy going in or out to the grid. So with this information, and the resolution is every 5 minutes. So we have this device able to send energy. It's connected by a Wi-Fi connection, and we send to a database, and we have data every 5 minutes. Regarding the information of the system, this is the rated power of the peak power of the PV system is 4.2 kilowatts, and the inverter is 3.3. And yes, the inverter is the smallest. We have flipping in summer because the limit is 3.3. Even the system is able to produce more energy. And we have a lead acid battery. This is not a lithium-ion battery. It's a lead acid battery. And also we have some. The capacity of the battery is 10 kilowatts hour, but we only could take profit of 80% of the energy. Because if we don't allow the battery, this is one of the limitations or one of the restrictions that we have in our system, and in order to increase the life of the battery. Okay, good job. Here you can see real pictures of the system. This is located on the rooftop. This is the rooftop. This is the flat. Okay, the inverter, batteries. Okay. So what else we are doing? We are also changing the typical curve. And how? We have to choose very critical loads. In this case, we have chosen the load that consume around 80% of the house. This is mainly the air conditioning, and this is a hot water heater. Okay, everything is, we don't have, the house is electrified, so they only consume electricity. So we have also a washing machine and dishwasher. So we are only control these components. So, how we optimize the system? We use genetic algorithm. This is more or less the concept. I'm going to explain how this works. We have an initial population. The population are the data, the available data. Also, there is a fitness evaluation. In this fitness, there is the algorithm evaluate all the potential solution, and the algorithm select the better solution. There is a score, and this is they choose the higher or the best score or the highest score. So after that, there is a reconstruction, recombination, and also this is called crossover. And after there is a random information, and with this is called a mutation. And finally, we have a solution. Okay. So, as probably you know, this algorithm is very interesting because we save time in order when we have to calculate. It focus on small regions, and the search space is very limited, so the time that it is spent to solve or to find a solution is smaller. So we have lower computational cost, and yeah, this is one of the advantages of the algorithm. So when we apply this algorithm to our system, we need a objective function. So we optimize minimizing the cost of the energy and the energy coming from the grid. This is more or less the same because we pay when we take energy from the grid, we take more energy, we pay more. But on the other hand, it is not the same because the cost of the energy is not the same at every hour during the day. So we have to consider there is a small difference because the optimization is not exactly the same. And also we have a lower bound and upper bound. This is the minimally maximum energy that we have to take from for instance, from the storage system. This is go to 20, the state of charge go from 20 to 100%. Also, we have to limit the energy taken from the utility grid. This is 4.5 kilowatts, and et cetera, et cetera. We introduce all the mutation rate, the population size, that this is 500, the mutation rate is 0.2, the crossover rate, this is 0.8. Okay, this is like the initial components of our, or the initial value that this is our inputs, let's say in this way. So we need all this information from the energy, the PV production, the energy going in and out of the storage system, the energy going in and out of the grid, the load, and the cost of the energy. And finally, we have the best solution. We compare the best solution with the base case, and we can estimate how the improvement of the system, how the system have improved. So what have been optimized in this case? This is the battery scheduling, the demand response, and the grid energy exchange. So I have mentioned that previously. So yeah, this is I have mentioned also the decision variable, the objective function. This is the minimize the energy cost and minimize the grid realigns. And the constraint, this is the state of the charge of the battery, demand response, grid power limits, and load schedule requirement. So as a result, we have as a result that this is the best case. Take into account that this is a small value because this is a house, and this is only 1 week. So we are able to reduce the consumption from the grid from 10 to 2 kilowatts hour. And also, what's happened? What happens here? Not me, I promise. Okay. So it is also possible to increase the cell consumption from 90. 90, this is a lot because we have battery, but we can increase this value and it can arrive to 97%. What does it mean? It means that this is almost an off-grid system because the dependency on the grid is only 3%. Okay? And regarding the energy storage system, we have that in the base case, we depend from the storage system 64%. We reduce the dependency. So maybe you are wondering why I reduce the dependency on the storage system. I want to use the storage system, but that's not completely true. Why? Because if I reduce the dependency on the storage system, it means that the life of the storage system will increase. So the idea is not use the storage system too much, and instead that I would like to consume energy when I have energy coming from the sun. This is to summarize. Okay, so you can see here the initial situation, and here you can see the storage system, the PV production, and the energy taken from the grid. So we clearly reduce the energy to be stored into the battery. We increase the energy used, the cell consumption, the energy coming from the PV system, and we reduce the the dependency on the grid a lot. This is reduced from almost from 10 to 3%. Okay, here you can see this is not completely clear, but you can see the comparison of all the scenarios. This is the base case, and when we minimize the net cost and we minimize the grid reliance. You can see here that we have some big consumption because the air conditioning consume a lot. So finally here you can see the reduction of the use of the battery. So this line here in green is the we charge the battery until almost 100%, and we reduce until 20%. With the new system, you use the battery less. This is reduced to 30% till 80% that day. So we reduce the use of the battery, which increase the life of the battery. And finally, this is like a sensitivity analysis. This is the base case. We reduce the dependency of the grids, and we increase the saving of the in money. To conclude, we can say that we have optimized the system, reducing the reliance of the grid till 80%. Yeah, the cell consumption is increased 90%. The batteries use has decreased 40%. Obviously, this is a previous work, because using when we use this kind of algorithm, it's easy. We don't have to train this is not an artificial neural network. We don't have to train the model. But in future work, we're thinking to do more things like seasonal and long-term analysis, multi-objective optimization, integrating other renewable energy systems. It will be very interesting if we add, for instance, a wind system and also electric vehicle. And we also can create a battery degradation modeling. We can compare it to other algorithms in order to know what of the algorithm give the best solution. And we have, it's possible to hybridize with other models. So thank you very much.
Thank you very much, Carlos, for your very interesting presentation. Are there any? I have my assistants, yes. They told me that he's a better chair than myself, so I need to bring him. Are there any questions? Yes.
Thank you very much for your very nice presentation. So my question is, in this case, you are considering only, so the source of energy comes from solar panels only, right? Or because if it was like wind as well, so this might be rather different, right? That's what you are planning to do. So yeah, if you had the mix, so I was wondering how you could conciliate the use of batteries as well. So, okay.
Okay, thank you very much for your question. Yes, in this particular case, we have considered only a PV system. This is like a simple case, let's say. And in our lab, because this is a real flat, in the future, in our lab, we have a wind system, and the idea in the future is integrate this wind system, because the change let's say that the PV system is predictable. We will know what will happen. In the case of a wind system, it is more difficult to predict what will happen. So the wind velocity changes quickly. So yeah, but this is possible to integrate a wind source in the model. So yeah. In this case, only PV, but it is possible to integrate a wind system on more energy sources, any kind of energy sources.
Thank you very much. Are there any other questions? I have actually a question for you. I mean, it is an interesting framework, the one that you developed. as a demand-side management of the system, and of course you support the self-consumption of the system. My question is, can it be applied also to other framework? Like can it be used also for, like, for example, demand response strategies and so on?
Yes, of course. Even we have applied here demand response. The idea was, when it's possible, to, for instance, in reality, we have two storage systems. One is the battery. This is the typical battery that we have in this kind of system. On the other hand, we have a water heater. So what we can do in this particular case to apply demand response without having problem is we have a storage energy, heat into the water system. So we can use electricity to increase the temperature of the water when we have sun. And after we can store this energy, and we can use it at night, or it depends the use that you have from the water. But yeah, this is possible, and this is the case. We have here an 80 liters storage. We can store as water. So we can increase the capacity. It's not too expensive to increase the capacity of the heater, and we can store more energy if it is necessary. For instance, this is for 3 people. This is enough with 80 liters deposit, but it is possible to increase. And what will happen in this case? We are applying demand response, because instead to use energy during night, we are using energy during day. So we can apply to everything, to electric vehicle, to anything. Okay?
Thank you very much,
Carlos.
Very,
Thank you.
very impressive. Thank you very much. Vieni qua vicino. Okay. Oh, sorry, too many microphones. Okay, we just moved to our last presentation for this morning. There has been a little change, slightly change again. Our next speaker is Professor Maria Mandalaki from the Technical University of Crete, who will present us a paper is integrating hybrid solar technologies in building in Mediterranean region, the balance of passive and active energy design. Thank you very much. Please, the floor is yours. Okay, you need to stay here. Do not push this black. Black is Armageddon. Okay.
Okay.
Okay. Thank you. Please. Thank you. Basta. Bravo, Giovanni. Bravo.
Okay. Good morning. I prefer to take this. So I'm Maria Mandalaki, as Mattia said. Thank you, Mattia, for the introduction. I'm an architect and professor at the Technical University of Crete in the School of Architecture. So we move in another direction, let's say, concerning the building sector and the energy conservation. As we saw today, how crucial this subject is. For architects, and it's very crucial how to deal with a balance between this energy reduction of the buildings, and especially how to deal with the design of it, and the balance between the active systems and the passive design that we can design for our buildings. Especially for the cases that we have of existing buildings. It's very delicate subject because we need to achieve indoor microclimate stability, minimize the environmental impact, and preserve the architectural heritage, or preserve the architectural building at the same time. So in this presentation, we will see how a balanced design, active actually, and design and passive strategy can be improved by an appropriate thermal insulation as well as a strategy for possible economic and energy benefits. We will talk about a case study that is actually a building that we presented in previous SHERLOCK conference in Crete, that it was 2 years ago. I will do a brief introduction of that. It is a building of Mediterranean Agronomic Institute in Hania, and we need to energy renovate it and upgrade the function and transform it into the Mediterranean seed bank for one of the Mediterranean seed banks for Europe. So the building was, you can see it here in the. You can see here in the area of the Mediterranean Agronomic Institute, and here is a building. Actually, it's a T-shaped building, about 800 square meters, and the first proposition of balancing active and passive system was the integration of PV panels on the roof and the installation of a geothermal heat pump for the supporting heating and cooling for the building and the electricity. This was the active system. And the passive system we proposed, because it is actually a stone building, so we need to preserve this structure. We propose a trom wall in the south side of the building. Here you see the south facade of the building, and propose air exhaust chimneys at the center one, because due to its shape, this positioning of these systems was very beneficial for the exhausting air of the whole of the building. Here you can see the two sections and how they function. I won't take in details in that point, because it's not the subject. Further on, we're starting to see what are the benefits for the choosing the appropriate thermal insulation. Here you see the research methodology, actually, that it was already done with the previous paper, and how we simulate the energy. In that phase, we found out that we had 67% of energy benefits due to the passive systems installed already. And then we go to dynamic simulations to see what we're going to have further on according to the thermal insulation installed. We examined 3 scenarios, actually. From here you see in 3 lines, the columns, the scenarios. The first concerns the XPS insulation, conventional one. The second, a perlite mineral insulation. And the third scenario, it's completely bio-based insulation with straw clay. If you see the properties of the material, you see that straw clay has lower and higher thermal conductivity, and this led us to the propositioning of much more width. Instead of 5 centimeters of XPS that we propose 10 centimeters of thermal insulation for the case of straw clay. So here you see actually the results. The baseline scenario is the one that it's an uninsulated building before, and then we have the three results with the XPS and the perlite and the straw clay. What is very important is that despite of the difference in their properties, the panel of straw clay was giving better performance in the building. So what I want to say is that it's very important that the simulation is the dynamic simulation actually is showing that even if the straw clay panel is having lower performance because it allows the heat mass of the building to perform a react because it's a breathable insulation. This finalizes in a better performance of the whole building. As you see in the numbers, here there are, of course, different ways of constructing these straw clay panels. There are also industrial ones, and there are also self-structure panels as well. We propose, because the distance of this of transportation, it was too high to propose an industrial one. We propose the self-structure panels. And further on, the one thing that we saw is that the panels are performing better in terms of energy. The other thing is what is the carbon footprint for all these materials, because they are local. The straw is local produced material, and there is some CO2 emissions that are the materials producing anyway. So the first thing was the operational. We saw in the previous slide that the operational energy was diminished, and the second thing is the embodied energy of the thermal insulation of these three types of thermal insulations. So the carbon footprint for the XPS, it's much more higher. We see that we have a negative carbon footprint for the clay straw insulation due to the absorption of the CO2 emissions that it has while growing. So we are starting in a better, let's say, level in terms of energy consumption for producing this insulation. So here we see all the data collected. The operational energy and the operational CO2 emissions per year for each of the scenarios that we don't have. We have XPS and straw clay much in the same level. We have the embodied energy of for production of the XPS and straw clay, especially this big difference. So we have this total carbon footprint for the three scenarios, and we see this big difference between the XPS and the straw clay material, straw clay panel that is produced locally. If we see further on for the economics benefits of this proposition, is of course that we have an economic benefit from the straw clay panels, even if we calculated the installation cost for each of these three scenarios. Actually, the financial savings are higher for the physical one, the natural material. The per lead scenario, it goes, even if it's more environmentally friendly, it goes higher due to the installation cost, the higher installation cost than the conventional one. And if we consider that we would have subsidy for these types of materials, that is the future, we can have that in 12 years, as you see here, we can have very good benefit, economical benefit for this proposition. So finally, if we want to conclude, actually, is not that we can always propose these types of integration of insulation or of passive system, that the energy management of each building, and especially the retrofitting, needs to be balanced every time, and that is very crucial that we will have simulations that can absorb this knowledge. Of course, the transition for KENAC actually in Greece is very crucial because it doesn't incorporate, it has only static U values, and we need dynamic carbon intensity and thermal capacities indicators in order to transform to this bio insulating materials. Of course, there are also some limits. In conclusion, the MAIH seed bank demonstrate that this strategic planning can be future, or can be a way of examining the renovation of especially stone buildings, or especially buildings that they have this thermal mass already. So we propose this as a blueprint for the next generation of zero carbon buildings transformation in Mediterranean. And we hope that we can continue this type of research concerning the better dynamic way of examining the energy upgrades of buildings in Mediterranean. Thank you very much.
Okay, thank you very much, Maria, for your very interesting presentation. Are there any questions? Yeah. Guarda. Annalisa, vai. Veloce.
Grazie. Thank you for your presentation. I was wondering, why did you decide to pick 60% as the public substitute?
Yeah, that's a good question, because there are already some programs in Greece that they subsidize energy upgrade of buildings, and they are in this range. That's why we thought maybe it's, I mean, we can have this in these programs as well.
Thank you so much.
Welcome.
Okay, thank you very much. We are a bit delayed. I apologize for that. So I think we can move for the coffee break. And thank you for staying with us in this first session. We will continue later after the coffee break with other presentations. I just want to ask the SHERLOCK partners if they can stay here for 2 minutes. We will take a picture. Thank you very much again.
My name is Jorge Facão. I'm working in Portugal at LNEG. I'm the director of a solar energy laboratory, testing laboratory to test solar systems and components. And I'm also part of the team of the SHERLOCK project here in Portugal at LNEG. Yeah, I'm the chair for this presentation. So the first presentation, I think, is from Vicenzo, yes? It's not according to my program, but I think there was a change. So Vicenzo, please, the floor is yours.
So, good morning, everybody. Here I am with my assistant, Giovanni, and I'm going to present a paper entitled Enhancing Cooling Degree Days Estimation, a novel method embedding solar and atmospheric effects. Okay, so, first of all, let's say that it's known in literature that heating degree days and energy consumption for winter heating are very well correlated. And here you can see from the chart how this correlation is quite good, and it is a linear correlation. The problem is to understand if the same considerations can be applied to cooling degree days for cooling buildings. Because as we are experiencing, cooling is becoming very demanding problems in many European countries, including Lisbon. As Laura told us last week, here there were 40 Celsius degrees. So the cooling of buildings is becoming a very hot and relevant topic. The answer is that CDDs and the cooling demands are not very well correlated, because cooling degree days only consider the impact of temperature. But we know that temperature is not the only parameter that is relevant for the cooling, but we need to consider especially the solar radiation. So the idea is to try to understand if it is possible to improve the description of the cooling degree days. It is possible. It is possible. There are models. Here there is I report a paper that we published in 2014 of also Mattia was author of this presentation. But the problem is to find an easy way to correct the degree days, the cooling degree days. Because if we propose complex modifications, complex corrections, they will not be used in the professional practice. And instead, here we want to propose something that is easily applicable, that designers can use as they use the heating degree days, at least for preliminary designs. So, let's see which is the proposed methodology. Here you see the descriptions of cooling degree days and heating degree days. You can see standard descriptions. And on your right, you can see the modifications that is proposed. Instead of using the air temperature, let's say, this air temperature is modified by embedding the solar radiation and the radiation to the sky. So two correction terms are embedded. And this correction is very simple, because the idea is to use to propose a simple corrections based on data that are simply available. And you can see that the air is the temperature of the external air that you can retrieve for meteo data. G is the total solar radiation on a horizontal surface. Alpha is the absorption coefficient of a building wall. HW is the convection coefficient, and then you have the other terms, Q dot sky divided by HW, which represents the radiation to the sky. And again, Q dot sky can be calculated in a very simple way. I show you in a moment. So, meteo data are taken from free and available databases. For example, from the PVGIS database that provides you data about solar radiation, temperature, and so on. Then there are some assumptions that you can see here listed, like the solar absorption coefficient of a wall, the wall emissivity, view factor to the sky, and so on. These are assumptions, but these are the normal assumptions you do also when you want to develop a dynamic model. So it's not something specifically needed for this modification, but it is something that you would do in any case if you, for example, develop a more precise dynamic model. Then some estimations must be done, like the sky temperature, the external convection coefficient, the radiation heat exchange coefficient, and then the sol-air-sky temperature. But these estimations, again, are quite standard because there are correlations for the sky temperature, correlations for the external convection coefficient, or for the radiation heat exchange coefficient, and so on. And again, these are the classical and typical correlations you can find in the dynamic models that we usually do, like can be energy plastics, can be transits, and so on. Exactly the same correlations. So let me show some preliminary results. So first of all, you can see the difference when we modify the heating degree days and the cooling degree days with the procedure I proposed. You can see that the impact on the heating degree days is more or less limited. Here, the data are compared with the public databases. Eurostat publishes directly the heating degree days and the cooling degree days. Instead, from PVGIS, you can fix the base temperature, you have the air temperature data, and you can calculate the heating degree days. You can see that the test is done in 3 Italian cities. So in terms of heating degree days, there are some differences, but not that much. But when we move to the cooling degree days, you can see that the difference is huge. So if the difference is huge in terms of cooling degree days, you will have a huge difference also in terms of cooling load that you are going to estimate. And here you can see the heating load and the cooling load. So you can see different calculations. You can see what happens with the modified degree days that I am proposed. You can see the results of a dynamic simulation that we can consider the benchmark because it's the most precise calculation we can do. And you can see the results between the results obtained by using PVGIS data and Eurostat data. So the red histograms represent the demand for heating. And you can see that even though there are differences, more or less they are comparable. Whatever approach you use, more or less they are comparable. But when we move to the cooling load, we can see that if we use a standard description of cooling degree days, the results are completely far from the benchmark that is the dynamic estimation. Instead, if we compare the modified approach with the dynamic simulation, we can see that the difference is much less. And then the correction of the degree days seems to work, at least in the case of Milan. Here we have the case of Turin. In the case of Bologna, the same. So with an overall simple correction, we can increase much more the precision of a very simple methodology, because to estimate the cooling load, we can just consider the thermal conductance times the area times the hours of cooling or heating and the amount of cooling degree days for that location. So the improvement is noticeable. In conclusions, so the proposed paper simply suggest a very simple methodology to correct the cooling degree days. This simple correction, however, improves the accuracy very much. The issue now is to test this methodology in much more different climatic conditions, because here, for the sake of the conference, we made the calculations for 3-4 cities in Italy, and for sure we need to extend to a largest amount of cities in order to try to have a better validation of the methodology. So, thank you very much for the attention.
So thank you, Vincenzo, for your nice presentation. If you have some questions for Vincenzo, we'll go to.
Yes.
Grazie. So thank you for the very interesting presentation. I have 2 questions. One is, so you added basically 2 parameters to the air temperature. And do you know how much each of those affect the temperature? Can you go back to the formula, maybe?
If I manage.
I mean, if it doesn't, because you added 2 parameters, the one for the radiation and the one for the sky. How differently do they affect the output number for the cooling degree?
The radiation affects much more the problem, the sky much less. But since it's not so complicated to determine also the sky correction, I decided to include. But let's say that 80% is I mean, the solar terms affects by the 80%, the sky by 20%. Okay, so this is the proportion, more or less. But since I mean 20% is an amount that is not exactly negligible, and since the calculation is easy, I just included also the sky part inside the correction. Let me also notice that solar air temperature is well known. You can find it in literature, and sometimes also the correction with the sky you can find in literature. But it has never been used to calculate the cooling degree days.
Thank you. It was just a curiosity. And then, I mean, you mentioned this already about the city selection. Maybe you chose cities on the northern side of Italy. Maybe analyzing Naples or Palermo will be interesting as well. So,
Yes, it will be interesting as well. But why we choose cities in northern part of Italy? Because you say, okay, northern part of Italy, we don't need cooling, or we need less cooling. Actually, the paradigm is a kind of switching, because in cities like Milan, like Turin, the effect of solar radiation is becoming increasingly consistent. So it's quite obvious that if you move to southern part of Italy, the solar radiation has an impact, because it's warmer, climatic conditions are warmer. It's less obvious when you do the calculation in Milan and you see that everything changes.
I agree. Also, I think there is a behavioral aspect to that. Maybe you're in the south, nearby the sea, and instead of using the cooling, you go to the beach. So maybe that's maybe yeah. I know that's
in terms of mitigating, the impact. Yes, for sure.
Okay, thank you so much.
You're welcome.
You have more questions for Vincenzo? I have just one question shortly. If you intend to analyze other countries in the world, like for example the Sun Belt region of Europe or world, Africa.
No, the idea actually could be to reproduce the first picture I did, where for heating degree days, we basically analyzed many cities in Europe, all the Europe. And the idea could be to make the same analysis, so to extend all the calculations for the same amount of cities in Europe, so from Cyprus to Northern Europe, Portugal, and everything. You are welcome.
So let's move for the another speaker. So the another speaker, according to my program, is let me check. Martina, yes. Martina from University of Geneva. Please, Annalisa, introduce yourself, and the floor is yours.
Good morning, everyone. I'm Annalisa Bringiotti, and today I'm presenting the work that we have done together with Martina, Mattia, and another Annalisa. The title of our study is Energy Flow Dynamics and Management Strategies in Renewable Energy Communities. The main motivation of this study was to try to give an answer to this simple question. So, is joining a renewable energy community really beneficial? Okay, if we think about this question, we have to think about the actors. So we can have three different actors. The first one are people. So if we think about people, to understand if for them is beneficial participate to a renewable energy community, we have to think about comfort, energy autonomy, and also the electricity bill. If we think about the power system, the variables obviously change it. So for the power system, it's beneficial to participate to a renewable energy community if we can have a certain amount of voltage, a certain specific amount of voltage profile, if we can manage and control the grid import, and if we can have some power quality. And last but not least, if we think about the planet, it's beneficial for the planet to increase the use of renewable energy communities if we can compute and reduce the CO2 emissions, the primary energy consumption, and increase the renewable energy sources utilization. So the main goal of this study was to understand if it's beneficial or not. And to quantify this advantage, we decided to develop two different algorithms. The first one is a standalone algorithm. So we consider different buildings alone. So some of them can have some PV systems, some of them can have battery, and some of them does not have anything. And the second algorithm that we have developed is an energy community algorithm. So different buildings are communicating and are sharing the energy. The case study that we have analyzed is an energy community located in La Spezia in Italy, and is composed by 34 prosumers, 12 consumers, and 1 producer. So first of all, what we have done, we have conducted an hourly energy analysis. So we have considered the hourly load for some residential buildings, educational buildings, working buildings, and also for one supermarket. We have modeled the PV systems with the simple equations considering the radiation from PVGs as well. And we have also modeled the battery energy storage system. Considering the first algorithm, that is the standalone, the main equation that is implemented in this algorithm is an energy balance equation, considering the different amount that we can have for import and export from the grid, charging and discharging of the battery, and the PV generation. In this, considering using this algorithm, this algorithm is able to understand and to compute two different operational conditions. The first one is the surplus, and the second one is the deficit. So if we are in surplus, it means that we have more PV production than the demand, so we can sell to the power system the certain amount of energy that we don't use. And if we are in deficit, we have for sure to buy the electricity from the power system. Here you can find some of the results that we found with the standalone algorithm. You can see the differences. These are the graphs just for two houses, a detached house and a multifamily building. But we have the results for every type of user that is inside of the community. And what you can see is that I mean, you can see the differences between winter and summer for sure in terms of PV production, and you can also see the differences in the battery energy storage use. For what concerns the renewable energy community algorithm, this is the flow chart. Again, the energy balance is the main equation, and it's the main rule of the that we consider. But in this case, first of all, we did a single user analysis, and after, if an user is in the case of surplus, for example, instead of selling the energy to the power system, is giving this energy to the community, and is divided proportionally to every user. This logic can be also changed, but for now we have decided to divide it proportionally. In these slides, you can see the results that we found for again the same users, so the detached house and the multifamily house. And what you can see is that in this graph we have a new color, let's say, so a green area that is the electricity that is coming from the renewable energy community, and so we are reducing the electricity that is imported from the electrical grid. Here you can see other users that are inside of the renewable energy community. For example, the high school that has a big amount of PV panels, so is able to cover its load just with the PV and also with the battery. You can see also the offices that don't have, for in this case, PV power and BESS, and the supermarket that has both. So if we go on with the results and we speak about the benefits, if we speak about people, at the beginning I show you that we can look on different variables, but for sure one variable that is really important for people is the electricity bill. So we have compared the electricity bill for every user that is inside of the energy community, and in this case we have comparing these two type of algorithms, we are having electricity bill reduction, and there is a difference also between summer and winter. For example, in summer we have a 6% reduction, and in winter 8% for this house. This again is the detached house, and if we consider a different user, we have a different reduction. But for every user of the energy community, we are having a reduction in the electricity grid. So it is beneficial for users to be part of a renewable energy community. If we speak about power system, as I was saying before, the main quantity that is important to analyze is the energy, in particular is the grid import. So we have, for example, this is just an example, but it works for every user of the community. If we consider the multifamily building during a summer week, for example, just with the standalone algorithm, so the first one, we have a grid import during 1 week that is more or less, in this case, 54%. But if we increase the algorithm and we include also the renewable energy community logic, we decrease the grid import, and in this case is 43%. And if we speak about the planet, for sure we have to consider some environmental variables. In this case, we have computed the CO2 emissions. And again, since the grid import is less, also the CO2 emissions will be less in this case, because we are using more PV panels and batteries, so let's say renewable energy. And for both houses, we can see that we have a decrease in the kilograms of CO2 that are emitted per day, so per week, and so on. So just to conclude, this was a preliminary work, and yeah, the main idea was to confirm again if joining a renewable energy community was beneficial or not. So we can say that if we speak about people, yes, it's beneficial because it's possible to reduce the electricity bill. If we speak about the power system, we can say that it's beneficial because we reduce the grid stress. And if we speak about the planet, again, we can say that it's beneficial because we can reduce the CO2 emissions. Future works will focus on a more accurate management of the battery energy storage. So we are thinking of including some logics of charging the battery during the low and electricity price hours and discharging it during the high electricity hours. And also we are thinking about adding an optimization to achieve an higher economic and energetic benefit, and also to minimize the grid import. Thank you so much for your attention.
Thank you for a nice presentation. If you have any question,
yes.
Just one question because you are in a hurry.
Thank you very much for your interesting presentation. Just a curiosity about the methodology that you adopted. You told us you developed two algorithms, standalone and a renewable energy community algorithms. Can you tell us more about the tools and the methodology you adopted to develop them?
Yeah. Yes, thank you for the question. Yes, sure. I mean, we have used Python to model them. Both algorithms are really fast computing. They are rule-based, so they have some limitations, but we have implemented some logic that allow us to charge the battery just if it's available some PV surplus. So there are some rules that the algorithm follows, but yes, future work will increase the accuracy of this algorithm. Thank you.
If we have more questions, it's better to discuss in the coffee break because we have no more time. Thank you.
Thank you.
So the next speaker is from Lithuania. I think Vytautas is the name. Yeah. So the subject is challenge and potential for integration of low-grade renewable energy sources technologies to the edge system in Lithuania. Please, the floor is yours.
Good morning, everyone. Thank you for the opportunity to be here and to represent our latest research topic on challenges and potential for integration low-grade renewable energy source technologies to district heating systems in Lithuania. And I'm Vytautas from Lithuanian District Heating Association. So first of all, I would like to introduce and emphasize the importance of decarbonization, which has become the major target of European energy policy, driven by the need to reduce greenhouse gas emissions and improve energy efficiency in building sector. This directions reinforces the need to integrate renewables and innovative technologies into existing district heating infrastructure. In addition, low temperature renewable energy waste heat sources such as ambient air, wastewater, industrial excess heat represent a significant but underutilized potential, particularly using advanced technologies such as high-capacity heat pumps and storage systems. However, their deployment is still constrained by economic, technical, and strategical challenges, highlighting the need for reliable methods to support better investment decisions and better system planning. And in order to stimulate this balance and efficient development of renewables for building decarbonization process, it is actually necessary to ensure robust planning of district heating system by implementing the reliable solutions. Yes. Therefore, the relevance of building decarbonization was directly linked to the separate small district heating boiler house in Kaunas region, which is the second largest city in Lithuania. And Neveronis separate district heating system currently faces several significant challenges, including high full dependence on natural gas throughout the year, high CO2 emissions, reaching more than 900 tons per year, and limited operational flexibility, geopolitical risks with gas supply, and other things. Therefore, the comprehensive heat production analysis was performed and organized in order to identify technically feasible and economically viable solution to replace natural gas and achieve at least 90% of renewable heat. And I would like to introduce everyone what is the current condition and status in this Neveronis separate district heating system. So this system serves 20 customers with a total heat load of 1.6 megawatt and consisting annual heat demand approximately 4,200 megawatt hours. The total installed boiler house capacity amounts to 5 megawatt, where entire heat generation is based on fossil fuels. And this research actually assesses and investigates the waste and ambient heat potential in the Neveronis area by evaluating available heat sources, technical potential, and economic feasibility. Our study investigates waste heat recovery from local wastewater treatment plant, nearby industrial facilities, possible river geothermal resources, and ambient air as potential heat sources for this existing boiler house upgrade. And the analysis concludes that although these several options show theoretical potential, significant technical, economic, and data-related uncertainties limit their implementation, ambient air emerges as the most practical and feasible heat source for future development. And the scenario analysis was performed using very well-known Energy Pro software, applying heat pump operation at the first priority level, aiming to reach 90% renewable energy production strategy at a local production balance. And in order to ensure maximum environmental protection, the preference was given for the use of natural refrigerants, A744, or in other words, CO2, which would be the most appropriate for medium-high temperature level on heatsink, reaching 85% supply temperature. And the scenario analysis was organized for mostly air-water compression heat pumps, focusing on identifying the optimal capacity and configuration of new heat sources. And with the help of Energy Pro software, 6 configuration scenarios were analyzed, incorporating diverse capacity combinations of CO2 heat pumps, storage, electric boilers, and biogas-based heat generation, as you can notice here. And such complex investigation allows us to reach and this analysis identified that scenario number 4 is the most financially viable option, comprising 0.7 megawatt air-water type compression heat pump combined with 60 cubic meter short-term storage. and it is worth to mention that such complex technologies enables annual heat production with efficient usage of compression heat pump operation and the best heat storage utilization, and having highest number of charges and discharges. It can also be noticed and observed that during the coldest periods, when outer temperature drops below zero or even lower, the heat pump potential output decreases accordingly. And demonstrate that operational indicators from heat pump operation meet more than 91%, 90% of total heat. The model seasonal COP of heat pump would reach 2.8 value, including all electrical devices and other stuff consumption. This new heat pump and storage would be used efficiently with a utilization rate of 54% and having operation time more than 5,000 hours per year at full out. And the remaining heat would be provided by using existing gas boilers infrastructure. Here, it can be noticed all economic assumptions, and the scenario analysis was organized based on these parameters for economic, assuming all the investment assumptions on heat pumps, storage, fixed and variable operational costs, and also according to the assumptions of upcoming 2030 period prices, including natural gas prices, electricity, and the outcome achieved indicates that all renewable-based heat production portfolio actually would have higher production costs compared to the existing natural gas boiler infrastructure. Nevertheless, the best economic outcome by implementing scenario number 4 in having investment in high parameters air-water CO2 type heat pump with thermal energy storage of 60 cubic meters, under which investment payback period might be achieved in 12 years. The total investment in heat pumps and storage equipment would amount to approximately 1.2 million without any financial support. And this results also demonstrate that the cost of heat production would be higher than existing natural gas boiler infrastructure in all years of equipment depreciation. And looking at 16 years perspective, it can be observed that average heat production costs would fluctuate around 7.5 cents kilowatt hour, which would higher per 1 cent per kilowatt hour when comparing the existing natural gas boiler infrastructure. But the situation might be absolutely different if we would include policy support mechanism, specifically 40% financial subsidy for this potential new investments in renewable energy-based heat production. And this measure was introduced to evaluate its impact on project feasibility and to support achievement of national targets for increasing the share of locally produced renewable heat. And it demonstrates that with this support mechanism, a payback period might be in only 8 years. It is possible to remain in line with the current heat production costs, and this support would not increase, would allow to reach the same heat price for final heat consumers, and this portfolio would also enable renewable based production in this separate district heating network. And in conclusion, I would like to emphasize the most important aspect, that is decarbonization of buildings achieved through the retrofitting of district heating systems should be considered as core element of national and European energy strategies. In particular, integrating low-grade renewable and waste heat sources with advanced technologies such as large-scale heat pumps and storage systems can significantly reduce dependence on fossil fuels and greenhouse gas emissions. The best among analyzed scenarios confirms that it is technically feasible to achieve a share of renewable heat exceeding 90%, which would allow a reduction of approximately 90% in CO2 emissions, while maintaining acceptable heat production costs under favorable policy conditions. Furthermore, it is worth to mention that integration of storage systems has proven to be a key factor in increasing system flexibility and optimization of operation of heat pumps. And in a broader perspective, the decarbonization of buildings through the transformation of district heating is not only a systemic transition that requires a coordinated development of energy infrastructure, regulatory frameworks, and financial support mechanisms. And the transition to decentralized and locally available renewable heat sources contributes not only to the achievement of climate goals, but also to geopolitical resilience and long-term price stability. So thank you for attention.
So thank you for your presentation. If you have any question.
So thank you for really interesting presentation and very detailed results. And while seeing your presentation, I had one worry that entered my head. That's, you say you would need to increase the price, the tariff, during the first years. So my question is, when the consumers see an increase in price, they may be incentivized to leave the district heating and to install an individual gas boiler for covering the heating needs. Because as we have seen, the prices you show, gas is definitely less expensive than electricity. So my question is there any law or any consideration in Lithuania that can limit the ability for disconnections until the price, the heat tariff here, reaches the same level as if they were using gas boilers?
Thank you for the question. Actually, yes, it might be some problems, and of course, for the final consumers, if in future the heat price might increase, but probably the main target is for operators, for investors to select the most appropriate option that would be feasible, economically viable, and will not increase the heat production cost. So always it should be applied the measures that would be acceptable and remain in line. We do not mention there are a lot of possibilities how to eliminate these bad factors. One of them we represented as financial subsidy. Another, there is better utilization of electrification tariffs. That is one of condition happening around our country, which facilitates better usage of such equipment. If, for instance, the same heat pump with storage would participate in the balancing market, this would allows to get a better economical results, indicators, payback period, and so on. So this is from this corner, but I don't know. Maybe you might ask other questions. Do I
That's
answer?
all I had. Thank you.
Mm-hmm.
So thank you for your presentation. I would like to apologize for the mistake with the names because there was a problem with my product. The last speaker is Pietro Luggi. And the title of the paper is Target Retrofit Strategies for the Decarbonization the Italian Detached House Stock. No? But you are... Okay. Okay. So you are not... Yeah, that is the presentation. What is yours? So far. No worries. Okay, hello everyone. Thank you very much for attending this presentation. I'm very happy to see familiar faces here today. I'm Lucas Martinez, a researcher at Polytechnic University of Valencia. It's okay right now? Okay. With the co-authors that you can read there, we conducted this study that I'm going to present today. And we are going to talk about the framework for designing local knowledge hubs. So we will go through this point. And just to contextualize the study, the energy transition is reshaping skills. It's demanding competencies in energy efficiency, renewable energies, and digitalization. So also we found that existing trainings remain fragmented and or misaligned with labor market needs. So we believe that these knowledge hubs can bridge that gap. So our research question here, how to design these knowledge hubs, and not only how to design them, but how to operationalize them and how to maintain, how to sustain them over time. So that is our target, that is our objective. And also to do it in a transferable way, so someone else, some other stakeholders in the future can use this knowledge to replicate these knowledge hubs. So this study is informed by an ongoing project, which is RESKILL, co-founded by the European Union, and we have 4 pilot countries where we are developing these knowledge hubs in Spain, Italy, Greece, and Ireland. So this is the overview of the framework we are proposing for creating these knowledge hubs, and we will go through some specific details of each one. First, the stakeholder ecosystem design, which is very important. Here, we need to create this network with different stakeholders at different knowledge, at different expertise, at different sectors to identify the skill gaps and the training needs. How we do that? With dialogue, conversation, interviews, surveys. All of these are necessary to gather this information and then also inform this with some best practices at the European level. Then a co-creation process goes through all the partners where we create and validate the micro-credentials. All this training we will provide for different stakeholders to upskilling and reskilling. And once they are validated, we go through the programs creation. Also an iterative process, we ideate, we iterate, we validate, and then it's ready to go in an open access format for the different trainings. And this is how we are proposing to maintain
this network, how to govern it. So we divided it in different functional units, starting with an external advisory board, specialists from industry and academia. And then we have a management board in the project that provides a strategic direction to a management office, and this management office provides a clear guidance for the different knowledge hubs. Once in the knowledge hubs, we implement the activities, we create knowledge that feed back the loop and feed back with information to the other different functional units. So these are our final products, what we expect with this knowledge, with this project. First, to create the local knowledge hubs, then to identify these skill gaps, the training needs, and to provide with the necessary and sufficient training to bridge this gap through micro-credentials that will be published online, and then also to complement all this training with innovative tools such as AI, gamification, co-creation processes, board games, and so on. And with all of this, provide a proper educational training for different stakeholders that are trained, and then that provide services to the building energy sector that at the same time will provide a better performance in the construction sector, so the final result will be better cities where we live. Does it make sense? So this is the final product that we are expecting with this project in another format. This is how the micro-credential looks like in an open source, in an open online format, in an open access format. And these are the basket of the different micro-credentials created. And also some result of some surveys. We don't have time to go into the details of this survey result, but later you can take a look in the full paper. But I wanted to give you some insight from the Spanish Knowledge Hub. This is our hub. It's made up by different public organizations, private companies, trade unions, self-employed people. All together, we are creating this knowledge hub because we cannot do it by our own. We need to go there outside and create a network. And when we were preparing some workshops, we found these very relevant numbers. This is a current status of the energy sector in Spain. Only the youth employment represents only 21%. If we are talking about women, they represent only 32%. And these figures are even worse if we go to upper senior management position, where women only represent 9%. In the other hubs, the numbers are not very promising as well, and not even in a European level. So we said, okay, let's work on this. We are taking the energy transition very seriously. We want to drive an energy transition in the city, a transformative energy transition. Here you can take a look at our foundational, enabling, and supported objectives. And we said, okay, let's go and work in it. So here you can see some activities we conducted so far: educational resources and awareness seminars, decarbonization seminars online, on live format, some workshops in academia, workshops in high schools, and also boot camps, where these are very intensive training for different stakeholders, where they go, we take very close, we do a deep dive into the theoretical foundation, very complex processes, and then we go to hands-on exercises. For example, here, we visited a hybrid renewable energy laboratory we have in our university. We teach them how to manage the different renewable energy resources with battery energy storage system, how to operate the system, how to gather this data, how to understand this data, how to design these systems. Very relevant trainings for us as well. And just some insight from the last bootcamp we created, we had participants at different ages, 40 years old, 50 years old, 60 years old, that then they were asking, okay, how can I volunteer? That was a very insightful aspect for us in our bootcamps. So As a conclusion, not conclusion at all, but some lesson learned so far in the creation of these local knowledge hubs. I think it's very important a continuous mapping of stakeholders to show them what are the benefits of all these local knowledge hubs, otherwise they will leave. Then, to engage educator very early in the processes, so we have a slot in their academic calendar, in their agendas, so we can go there and provide training. Also to perform regular events, to keep momentum in the network, to maintain them motivated, and also remain flexible with an open-minded, so we can adapt the activities based on the stakeholders' input, and maintain a continuous communication that is also very relevant, and also recognize and celebrate shared achievement. As I said before, this is a project, an ongoing project, a project that is still alive, and we hope to learn much more and share it in the near future. So just I wanted to say, to acknowledge that the RESKILL project that was co-founded by the European Union and all these partners which we are working together, and I had the pleasure to be working with all of them. Some of them are present here, so thank you very much. Muito obrigado pela sua atenção.
Lucas, for your presentation. Not you can.
Yeah, I mean, I'm curious to ask you which is the reaction of the industrial stakeholders, if they are involved, they keep interested in the project, or you need to, work a lot on them to engage and to keep them engaged.
Which sector? Sorry, I didn't.
Industrial.
The industrial sector. Well, I think that here, at least in the Spanish Knowledge Hub, we had the opportunity to participate in different conferences of the industrial level. So because of different connections between the university and the governmental bodies, they are giving us some spaces as academia, as we should work together in a binomial format, because they understood through many conversations and discussions throughout the years that we need to work together. Finally, we understood that what happened to the university happens to the city and the industries, and vice versa. So that is a clear concept in Valencia, and I think they are listening to us. We are going there, we are doing our presentations, people is engaging with what we are proposing, with our micro-credentials, with our trainings, with our boot camps, with our services, and I think that is something very nice. Of course, there is a lot of work to do. And also another way to cooperate with industries, I think that is through catedras. We call it cátedras. So some chairs in the universities. I think that is how we are managing, also providing some students for doing practices, internships with the different industries. That is how we are finding this interconnection.
Thank you, Lucas.
Okay.
Now it's the last speaker. Sorry for the mistake. Is Pietro, and the subject is target retrofit strategies for the discovery innovation. The Italian detached house. The floor is yours.
Good morning, everyone. I know you're hungry, so I will try to be fast. So this is more a framework for targeted retrofit strategies. Okay, next. This is the talk outline. We will start with the policy targets, which is the base of this study. Looking at the targets we are a lot below the renovation rate we need to have to meet those targets. In this case, we have the Fit for 55 by 2030, which is a reduction of more than half of the emissions, and then the worst performing building directive. Okay, so this is the main issue we are trying to address with this study. We are doing this focusing on the residential sector. As you can see, is pretty relevant, but one thing that the data available we have is missing is the fact that in the first graph is the emission related by sector, and the residential portion does not account for the electricity, and in the second case is the total final energy consumption, but for residential buildings, most of the emissions come from the primary energy consumptions. So in this case, it's very difficult to evaluate. And then the third issue that causes uncertainty, for example, in this case in Italy, are all the households equal in Italy? They are not. A large portion of the stock is old, it's very heterogeneous, and the heating system used, which account for most of the emissions for the building sector, represent a wide variety in it. Proceeding with the methodology, starting from modeling the actual residential sector in terms of types, number, and what fuels buildings have. And then from there, how do we estimate the emissions from that residential sector characterization? Here we can see a snapshot of how it's constructed using official sources like Tabula, Istat, and the SECAP, using the three main KPIs, which are the main factor affecting the energy consumption and therefore the emission of the buildings, being the age of the building, which determines the thermal properties, the type of building, which represents the thermodynamics, and then the heating fuel, which represents the emissions related to the consumption. After this, we try to find, like in the table you see at the bottom, the values of how many of those buildings there are, the average number of occupants, and the size of those buildings, creating a total of 112 rows per city. We are analyzing five cities across Italy, which has a very wide climate condition across the peninsula. And it's already divided in climate zone reported by the SECAP. Okay. After that, we proceed with the energy modeling, starting from the heat losses, analyzing all the heat fluxes. After that, we estimate the appliance load, which directly correlates to the internal gains. And after that, we use the heating losses to size the heating system used and the energy consumption from this. So we have the energy consumption of the heating system and the appliances at the end. And then finally, no, in this case, I don't use the PV panel. And then finally, from there we estimate the emissions, which needs to be estimated in different way. From fuel, it can be done directly. And then for electricity, it needs to account for the grid, and then for the electricity production itself. All of these, as you can tell, a lot of those parameters are affected by uncertainty, so we use the probabilistic analysis, which allow us to use a range of inputs to get a range of output, to address all the uncertainty variables like the thermal, the geometric, the climate inputs we have for this bottom-up analysis. So I have a question for you if you want to answer, or I should skip this. Okay. These are the results. And as you can see, on the left, we have the Lorentz curve representing the dotted line on the bottom is if the emission were linear with the presence of the buildings. And the bottom one, the upper one with the shade, is the actual emissions per presence of buildings. As you can see, the 55% emissions, which is not reduction of the policy, but I kept it for consistency, is a pretty wide range, but it tells the same story that emissions are disproportionately located in the residential sector. And then on the right, a heat map identifying the buildings which have the highest emissions, accounting for the size, for the number of them, and for that. So key takeaways, even if it's a large range, it tells the same story. So we can focus our efforts instead of needing to retrofit the whole residential sector to meet the European goals we have for environmental benefit. And here's some limitation of the study. For example, I'm not considering the cooling system, which, as Vincenzo said, is very important. But for constructing the residential sector, it was very difficult to identify which buildings have a cooling system, because around half of the buildings in Italy have them. So it was difficult to locate them. So future work is to integrate that. Couple this with retrofit analysis, analyzing different type of retrofit like insulation upgrade, electrification of the thermal load through heat pumps, and renewable energy production, as well as a financial analysis related to this. And that was all for me. I hope it was fast enough. And thank you so much for it.
Thank you, Pedro, for a nice presentation. Any question? We can close the section. Mattia, want to say something?
Thank you very much, everyone, for being with us today for this Sherlock event. I won't hold you any longer, so it's lunchtime. We are all very hungry, so thank you very much. And I hope you enjoyed the session. Do you want to say something? Hi.
Thank you very much.
Thank you, guys. Thank you.